In this section, we'll focus on a topic that is absolutely critical in every data-driven project, and that is data quality. And even if it sounds trivial at first, poor data quality remains one of the most frequent and underestimated pitfalls in practice. Data quality is a major concern in the vast majority of organizations, whether in the private sector or public administration. Poor data quality hinders process automation and makes collaboration between different IT systems difficult, if not impossible. Systems can only function seamlessly if they share a clean, consistent, and reliable data foundation. In reality, however, this is often far from the case. Data is rarely perfect. Missing values, inconsistencies, and outright errors are the norm, not the exception. And that's understandable. Data is an approximation of reality, just like models are. But it never represents reality perfectly. Let's take a look at the example shown on the right-hand side of the slide. Here we see a typical item master dataset. At first glance, it looks well structured. Item number, description, length, width, height, weight, packaging unit, and so on. But if you look closely, you'll immediately notice several glaring issues, highlighted in red. Take, for example, the rows with values like 1 or 999 in the fields for length, width, height, and weight. These are typical placeholder values, often entered temporarily when no correct data is available. However, such placeholders frequently remain in the system and end up in reports and analyses unnoticed. Why is this a problem? Quite simply, because these values can severely distort your calculations. Imagine you're dimensioning storage racks or bins, and you're basing your design on an item that allegedly measures 999 centimeters in length. Your entire layout would be oversized unnecessarily. Or a weight of 999 kilograms for a small pack of tissues. Obviously wrong, but if left uncorrected, this will ruin any calculations related to load capacity or picking efficiency. The real danger is that these errors often go unnoticed. In large data sets, such outliers are easily overlooked or dismissed as exceptions. But here's the thing. Systems work with what they're given. If your input data is flawed, even the best algorithms will produce wrong results. Another common issue is missing values. Often, fields are left blank when information is unavailable. The problem is, it's often unclear what this means. Does it mean the value is unknown, irrelevant, or was it simply forgotten? Without clear definitions, these gaps can lead to serious misinterpretations later in the process. Now, let me make something very clear. Poor data quality is not a sign of incompetence. It's a systemic issue. In many companies, data grows organically over years, sometimes decades, and different systems, migrations, changing responsibilities, and a lack of standards all contribute to this. As long as no one tries to run in-depth analyses on this data, the flaws often remain hidden. But the moment you want to automate processes or optimize systems, clean, consistent data becomes critical. And that's when the hard work of data cleansing begins. So how do we tackle this challenge? The first step is always a systematic data quality check. This involves reviewing the data for completeness, plausibility, and consistency. Specifically, you should ask questions like, are the values within realistic ranges? Is it plausible that a bottle of oil weighs 999 kilograms? Are there null values or placeholders like 0 that shouldn't be there? Are field lengths consistent? Are there outliers that deviate significantly from the norm? Are there suspiciously frequent default values like 1 or 999 that warrant further investigation? For this, it helps to automate your checks. You can write simple Python scripts that scan for anomalies or use Excel with conditional formatting to highlight outliers. For smaller datasets, tools like Power Query in Excel can be very effective for quick, repetitive cleaning tasks. But technical checks are only half the battle. A critical element is communication with the customer. Many data issues can only be resolved through clarification. What might appear as an error to you could be correct in the customer's specific context, and vice versa. That's why early and ongoing feedback loops are essential. A practical recommendation: maintain a data quality log. Document every anomaly you find, how it was interpreted, and what corrective action was taken. This not only ensures traceability, but also helps build a reusable knowledge base for future projects. One last point: data quality is never absolute. Perfect data simply doesn't exist. The goal is not perfection, but achieving a level of quality that allows your analysis to yield reliable, actionable results. You're always working with an approximation of reality. The better the data quality, the closer that approximation gets to reality. In summary, poor data quality is one of the biggest challenges in practice. It's often the main reason why automation projects take longer and cost more than planned. But with a structured approach and good customer-approved assumptions, even imperfect data can be turned into useful information. Now, we'll take a deep dive into one of the most common and frustrating challenges in logistics data analysis: dealing with missing and faulty data. While the concept seems simple, its impact on system design, capacity planning, and overall project success cannot be overstated. You might think of this as just a data cleaning exercise, but in reality, it's one of the most consequential steps in any logistics engineering project. Let's begin by considering some of the typical situations you will encounter. Imagine you've received a master data file from a client, and now you're comparing it to the order data they provided. One of the first things you'll notice is that certain items appear in the master data, but are completely missing from the order data. This might seem odd at first, but before raising any alarms, you should ask yourself a few diagnostic questions. For instance, is the order data covering a sufficiently long time period? If you're only looking at data from the past month, maybe those items simply haven't been sold recently. They might be slow movers or even obsolete products that haven't been ordered in a long time. In such cases, it's often reasonable to ignore these discrepancies unless a significant number of items are affected. If it's just a few old SKUs, you can probably move on. But if entire product groups are missing, you may want to check back with the client. The reverse situation, however, often is far more serious. If you find items in the order data that don't appear in the master data, you may have a real problem. This may indicate that the master data is incomplete. The moment you detect this, you should be aware that your data integrity may be compromised. Why is this a big deal? Because automation of processes, whether that's warehouse automation, replenishment algorithms, or even simple reporting, relies on consistent, accurate master data. If the order data references SKUs that have no corresponding entries in the master data, you can't retrieve essential information like item dimensions, weight, or storage requirements. This affects not just one process, but cascades through every downstream activity. With that said, it might also not be a problem at all. The reason for having order lines with SKUs that do not appear in the master data could be that the master data is a recent cleaned up snapshot, while the order data includes historical data that includes products that aren't sold any longer and thus are not in the latest version of the master data. Make sure you ask your client, is this the case should you encounter such a situation? Now let's talk about a third category of problem: implausible or missing item dimensions. You'll often find data entries where critical fields like length, width, height, or weight are either missing or contain obviously incorrect values. For example, a weight of 0 kilograms or a pallet height of 999 centimeters. These anomalies need to be handled systematically. A pragmatic, widespread approach is to classify the severity of the problem based on the share of affected items. If less than 5% of items have such issues, you can usually manage this with simple workarounds or assumptions. Between 5 and 10%, you're entering a gray zone. At this point, it's essential to discuss the implications with the client. Anything beyond 10% is a red flag. When more than 10% of your data has critical flaws, you simply don't have a reliable foundation for detailed analysis. In such cases, you must establish explicit assumptions, ideally documented and agreed upon in writing with the client. This protects you later on when results are challenged, and it ensures transparency in the engineering process. Now, I strongly recommend we also look at the number, and especially the share, of order lines affected. If 5% of products in the item master have missing dimensions, but these 5% are not of interest because they have not been sold in 5 years, then who cares? If, however, the top 1% of fast-moving products have faulty data, that's far more important. In addition to these common situations, you should always perform a thorough plausibility check on your data. This involves looking for entries where weight, length, width, or height are empty or equal to 0. Such values usually indicate data entry errors or system export issues. But you should also be cautious with values of exactly 1. Often, when systems lack data, they default to a placeholder value of 1. This isn't necessarily wrong, but it's highly suspicious and warrants investigation. Another important step is identifying outliers. Look for items with extreme sizes or weights. For instance, if you're analyzing data for a food retail warehouse and suddenly encounter an item with a width of 300 centimeters, that should raise an eyebrow. Either the item is a very unusual product, perhaps a display rack or some form of special equipment, or the data is incorrect. The same applies to extremely heavy items. If you find a small consumer good listed with a density higher than gold or uranium, that's a clear sign something is wrong. Keep in mind that not all data errors are immediately visible. Logical flaws, those errors that seem plausible at first glance, are particularly dangerous. These are values that pass basic validation checks but don't make sense in context, or perhaps they even make sense, but they are still wrong. For example, a product might have correct-looking dimensions and weight, but when you analyze its storage category, it's assigned to the wrong picking area or storage zone. These kinds of mismatches are harder to detect because they require domain knowledge and contextual understanding. Let me give you a practical example. Imagine you're analyzing data for an e-commerce fulfillment center, and you notice that certain SKUs are assigned to a pallet picking area, even though their name clearly indicate they're small items, perhaps less than 10 centimeters in size. At a surface level, the data looks fine. No missing values, no zeros, no extreme outliers. But the assignment to the pallet area makes no sense. These are the kinds of errors that simple scripts won't catch. They require a human in the loop, someone who understands the business and the physical realities of warehouse operations. One very effective strategy is to build a simple dashboard that shows key data quality indicators at a glance. For instance, you might create a widget that displays the percentage of SKUs with missing dimensions, the number of order lines referencing unknown SKUs, or the distribution of item weights and volumes. This gives you and your client a quick overview of where the problems lie and how severe they are. Before we move on, let me emphasize one important point. data quality issues are not just technical problems, they are business problems. Flawed data leads to flawed decisions. If your storage calculations are off because of incorrect item dimensions, you'll end up designing a warehouse that either lacks capacity or is over-engineered, wasting valuable resources. Now that we've explored the common situations and challenges that arise from missing and faulty data, let's move one step further and discuss how to actually deal with these issues in practice. Specifically, we'll focus on understanding the impact of missing, incomplete, or implausible data on your analysis and decision-making process. The first and most critical step is to assess the extent of the problem. Simply put, you need to quantify how much of your dataset is affected. What share of data is missing or faulty? Is it 5%, 10%, or maybe just a handful of records? This might sound basic, but it's an essential diagnostic step. Without knowing the scope of the problem, you can't judge whether it's a minor nuisance or a major threat to the validity of your analysis. But it's not just about percentages. You also need to understand the nature of the affected data. What kind of articles are concerned? Are we talking about slow-moving items that barely show up in operations? Or are we dealing with fast-moving SKUs that represent a significant share of throughput? This distinction is crucial. Missing data on low-impact items might be tolerable. You can either ignore them or make reasonable assumptions without jeopardizing your overall analysis. But if the affected data relates to your high-volume, high-frequency products, the situation becomes far more serious. To make this more concrete, let's consider a simple example. Imagine you're analyzing order data for an e-commerce fulfillment center and you notice that 200 SKUs are missing item dimensions. At first glance, that sounds alarming. But then you check and realize that these SKUs account for only 0.5% of total order volume. In this case, you might decide to proceed by applying average dimensions as placeholders. The impact on your overall system design will be negligible. However, if those 200 SKUs represent 20% of daily throughput, you cannot afford to make such rough assumptions. Their absence would skew your storage calculations, distort your picking strategies, and lead to faulty capacity planning. Therefore, you need to analyze not just the share of affected data in absolute terms, but also its operational significance. So what can you do when faced with missing or implausible data? There are several options, each with its own trade-offs. One of the most common approaches is to overwrite implausible or missing dimensions with average values. This is a pragmatic solution, especially when the affected share is small. You simply calculate the average dimensions for items in the same product group, category, or packaging type and use these as proxy values. This method is quick, transparent, and often sufficient for high-level planning. Another option is to ignore, or rather exclude, insignificant items from your analysis. If certain SKUs have no data, but the contribution to throughput is negligible, you might choose to delete them from your dataset altogether. This reduces noise and simplifies your analysis. But of course, this decision should not be taken lightly. You need to make sure that these items are indeed insignificant and that their exclusion won't introduce bias. In both cases, documentation is key. Every assumption you make, every value you overwrite, and every item you exclude should be documented thoroughly. This ensures transparency, traceability, and allows others, including your client, to understand and verify your methodology. And this brings me to an absolutely critical point. Never proceed without client approval. Any assumptions you make to compensate for missing or faulty data must be validated and agreed upon with the customer. Ideally, this agreement should be in written form. This is not just a formality. It protects you from liability and ensures that all stakeholders are on the same page. Remember, bad data is not your fault, but mishandling it will be. To visualize this concept, the slide shows an illustrative example using the famous Mona Lisa painting. On the left, you see a version where data is simply missing. The face is obscured, like a blank canvas. This represents a situation where you have holes in your dataset, gaps that prevent you from seeing the full picture. On the right, you see what happens when you try to extrapolate from incomplete data without proper care. The missing parts have been filled in, but not in a meaningful way. The result is a distorted, almost cartoonish version of the original. This is exactly what happens when you apply flawed assumptions to compensate for missing data. You might think you've restored the full picture, but in reality, you've created a misleading representation that leads to wrong conclusions. This example highlights the inherent risk of bad extrapolation. Filling in missing data is not a neutral act. Every assumption you make carries the potential to introduce bias, to distort patterns, and to mislead decision makers. That's why it's so important to approach this task with methodological rigor and to involve the client in every critical decision. Now that we've covered the principles of dealing with missing and faulty data, let's look at a practical example. On this slide, we see a real case where missing data was detected and its impact was analyzed. Let me walk you through what happened here. The dataset in question consists of order data exported from a customer's system. Our goal was to cross-reference this transaction data, that is, actual order lines, with the master data, which contains item-specific information like dimensions, weights, packaging units, and so on. A very basic but important sanity check in this process is to ask, do all SKUs that appear in the order data also exist in the item master? You might think this should always be the case. After all, how can a product be ordered if it doesn't exist in the system? But in reality, this discrepancy happens more often than you might expect. On the right side of the slide, you see a code snippet that performs exactly this check. For those of you familiar with Python and Pandas, this should look pretty straightforward. The code essentially verifies whether every item ID from the order data is also found in the master data for two different data sources, e-commerce orders and LDC/OSS orders. In this specific example, the result is clear. For e-commerce orders, the check returns false. This means that not all items from the order data are present in the master data. In fact, as highlighted in the red box, there are 236 SKUs in the transaction data that cannot be found in the item master. At first glance, 236 missing SKUs might sound alarming. But as always, context matters. We need to ask, how significant are these SKUs in terms of operational impact? Are they fringe cases with negligible volumes, or do they represent a meaningful share of daily throughput? To answer this, the analysis goes one step further and looks at the number of order lines affected. The table at the bottom of the slide shows daily figures for a given observation period. For each day, we have 3 columns. OL count, the total number of order lines processed on that day. OLAM AF, the number of order lines affected, that is, containing SKUs not found in the master data. OL share, percent. The share of affected order lines relative to the total. Let's look at some of these numbers. On February 27th, we see that out of 261,565 order lines processed that day, 6,222 were affected by the missing SKUs. That's about 2.38% of all order lines. On other days, the impact varies. sometimes below 1%, sometimes close to 2%. While 2% might not sound like much, in a high-volume operation, this can represent thousands of items per day. Now, why does this matter? If these 236 SKUs were entirely irrelevant, obsolete products, items that were never actually shipped, or records with no operational consequence, we could simply ignore them. But if they represent active products that are moving through the warehouse, this data gap becomes critical. Without matching master data, we lack the necessary information to calculate storage requirements, optimize picking processes, or even validate basic operational KPIs. For example, how can you determine bin assignments without knowing the item's dimensions? How can you calculate throughput or space utilization without weights and volumes? Moreover, the absence of these SKUs in the master data signals a deeper integrity problem. If these items were ordered and processed but never made it into the item master, this suggests a breakdown in data governance. Perhaps new SKUs are being created in the ordering system without proper synchronization with the master database. Or perhaps product lifecycle management processes are not being followed. In either case, this discrepancy is a red flag that requires attention, not just for the current analysis, but also for long-term system stability. So what can we do when we encounter this situation? First, we need to bring this finding to the customer's attention. It's not enough to simply document the 236 missing SKUs. You need to discuss the possible reasons for this gap. Is it a matter of delayed data synchronization? Are there parallel systems that are not properly integrated? Or is it simply an oversight? Second, you need to assess whether it's feasible to retrieve or reconstruct the missing data. Sometimes this can be done by pulling records from alternative sources, for example from previous versions of the master data or from supplier data sheets. In other cases, you may have to make assumptions, such as applying average dimensions from similar items, but as we discussed earlier, such assumptions should only be made with explicit customer approval and thorough documentation. Third, you should quantify the operational impact of the missing data. For instance, calculate how the missing SKUs affect total storage volume estimates, picking frequency distributions, or throughput calculations. This helps the customer understand the potential risks and supports informed decision-making. Remember, it's always better to detect and address these issues early, rather than discovering them after a flawed design has already been implemented.